day of the conference. So the first speaker, we're very happy to have Enrico Pajer with us today. So Enrico, thank you very much for being here, especially given that the invitation was a bit late. So it's very nice that you managed to attend and to participate in this meeting. So I will just give you the floor and just remind you 5 minutes before the end that you have 5 minutes left. So please go ahead.
Perfect. Thank you very much for the opportunity to present my work here. Let me start by sharing the screen. Hopefully all goes well. Okay, yeah, so timeless history of time. The topic of the talk is to describe cosmology of the early universe, to some extent without mentioning time, although that's not really necessary, but it's going to be a very useful perspective to discover new structures that are otherwise hidden in the standard way of thinking about this problem. This is based on a series of recent papers that you see here on the right with a bunch of brilliant collaborators, so a lot of the credit goes to them as well. So I thought I would mention their name and faces: Sadra Yazayeri, who should be known to some of the Paris crowd, David Stefanizin and Scott Melville, all postdocs, and then 3 of my PhD students, Jakub Suppel, Harry Goodhue, and Gordon Lee, that did really an excellent work on this research directions. So let me start with some motivations. Mandatory, but I'll be brief because most of the people attending this conference have some interest in cosmology, and so a lot of the motivations are common to many of us. We think that cosmological observations of the late universe, perhaps surprisingly, but they probe quantum field theory on curved space-time at very high energies, as well as the perturbative regime of quantum gravity. And those are all things that we care about and would like to learn more. And so if we can get some hint from observations, that's going to help a lot. We know that the study of the primordial universe can be really a discovery machine. It can tell us about new degrees of freedom beyond the standard model, new parameters, new fundamental constant in physics. As far as we can tell, none of the scales associated with inflation can really be built out of standard model scales. So there is some new fundamental parameters of nature, and perhaps even can give us some hint on the UV completion of gravity. So in this talk, I'll present what I think has been enormous progress in the past 2 or 3 years in thinking about the early universe and how to make predictions from it from a completely different way than we were used to do previously, namely just based on fundamental principles such as unitarity, locality, and symmetry. And I should say I welcome everyone to make comments or questions during the talk. I think that the idea of the talk is very simple. Perhaps some of the formula are not as transparent, but just please feel free and stop me. So first of all, I thought just a lightning review of what it is that we observe when we're talking about the early universe, what are the observable that we would like to predict. And I think perhaps in one word, we would like to predict the wave function of the universe at the end of inflation. From that, you can extract everything you want. Any other prediction you care about can be extracted from basic quantum mechanical rules from that notion. So mathematically, if we assume the very early universe is well described by a quasi-de Sitter space-time, we really want the wave function, or rather the wave functional of the universe, depending on all the degrees of freedom of the universe. If there are extra scalar field or the standard model particles, the metric itself, everything in the universe should be one of the arguments of this wave functional. And we want to describe that at the future infinity of the Sitter space-time, which in conformal time is eta to 0, or in cosmological time is the t going to infinity. And for this whole talk, we're going to assume that we start from an initial condition, which is the most motivated, the most well-motivated that we have, which is the Bunch-Davis initial condition. But I think other choices are also possible, and similar discussions would apply, but I will not discuss that in this talk. So just to make it a little bit more explicit, if phi is the set of all fields that we have in our universe, both discovered and undiscovered, then the wave function of the universe is a functional of this field, and it can be written as the exponential of all possible powers of these fields with coefficients. And if I give you all those coefficients psi n, then I've given you all the wave function of the universe, and everything follows from that. If you want to compute any probability you want, which is what we want to predict, you just use the wave function, you put the operator there, and that's the expectation value. And so you can make any prediction you want. And we also, as we know very well from quantum mechanics, for example, we have a convenient way to compute this wave function, which is just a path integral. It's all the path from some vacuum to whatever you want at the end, weighted by e to the I, the action. Many of us that think about the early universe or are more used to think in terms of correlator, expectation values of fields, for example, temperature anisotropies or dark matter densities. All of those can be derived from this. And there is a one-to-one relation, which is pretty simple. For example, the 2-point function or power spectrum is just 1 over psi2, the quadratic coefficient. The 3-point function is just the real part of psi3. The 4-point function is related to psi4. And so every time I'm going to talk about this wave function coefficient, if you don't want to think too hard about it, just think of them as being correlators. That's a good enough approximation. There is a little difference, but you can just go from one to the other very simply. The reason why I insist talking about the wave function is because we will see many formula take a much simpler expressions when we talk about the psi rather than b, because we don't have to do this conversion. Okay, so we want to predict everything from the early universe. So how do we do it? There is a traditional way to make predictions in which you write down a theory, but we don't write down any theory. We would like the theory we write down to obey some fundamental principles that we have either make mathematical sense or that are extremely well tested. For example, if you want to make some prediction for colliders, you start with, say, well, this is a quantum theory, so it has to be unitary. Lorentz invariant is very well tested. And then you write down a series of models, for example, the standard model of particle physics, and you use that model to make prediction. And this is very, very useful, a way to proceed when you have a preferred theory, like general relativity or the standard model, because from that theory, you can make a lot of predictions. And for example, we can do that in the early universe as well. We know how to compute that using that path integral that I showed you before, how to compute every coefficient of the wave function. And they're given in perturbation theory by simple Feynman rules. You draw a diagram, time is running on the vertical axis. If you want the wave function for 5 fields, you draw all possible diagrams that end on 5 points. And every diagram you can associate it with a set of integrals through some Feynman rules. The details of these integrals are not so important, but it's just well known. Like you compute amplitudes, you can compute this wave function coefficient, and similarly correlators. Usually they are functions of external energies, functions of energies of the external particles, as well as the energies that run through the internal lines. And you can have 3-level diagram, loop diagrams, etc. This is a way to proceed and gives us result. However, it has some drawbacks. There is no one-to-one correspondence between Lagrangians and observables. There are many Lagrangians that describe the same observables. That's true also for particle physics. We have field redefinitions, degeneracies, and gauge symmetries, which have nothing to do with physics. In cosmology, even worse, because we don't observe the time evolution during inflation, there are many time evolutions that lead to the same wave function. So all those models are completely degenerate as far as observations are concerned. Even worse in cosmology, as I guess is well known, time translations are broken because the universe is expanding. It's different tomorrow from how it was yesterday. And so all the time integrals don't give you delta functions of energy conservation. You really have to do them. And that's a big pain. That's hard to compute. If you have V interactions in a diagram, you have to do V nested integrals. And this gets very complicated pretty quickly. The other issue is that you don't really see how fundamental principles come out into the result, because you use them to write the theory and then you take that theory to compute the predictions, but it's hard to know what the consequences are of unitarity or locality, and that's a drawback. More ambitiously, if you want to derive something that goes beyond perturbation theory, either non-perturbative in quantum field theory or even non-perturbative in quantum gravity, we need a much more fundamental approach to the problem in which we can learn from perturbation theory, but the lessons we learn from that should apply more broadly. For example, if we had a fully non-perturbative notion of unitarity, like the optical theorem for particle physics, we could make non-perturbative statements. And I think that's one of the most exciting goals of as far as physics of the early universe is concerned. So in this talk, I'm going to propose a different way to approach the problem, in which we completely bypass the idea of writing down models. We go straight from fundamental principles to observables. Our fundamental principles will be unitarity, because that's required for the mathematical consistency of the theory, some form of locality that I'll specify, and symmetries, and I'll exclusively rely on observed symmetries. And then we will see that those are already so powerful that completely constrain all possible observations that we can write down, all possible endpoint correlation functions. I think this is a very effective approach because we don't have a single model that is preferred. We have a very large number of models, and it is very impractical to compute the prediction of each one of those. So we might as well just write down the most generic result compatible with fundamental principles. So enough with the philosophy, and let me give you some results. First of all, symmetries are useful to set the problem. And observationally, we know the universe on large scales is homogeneous and isotropic, so invariant under translations and rotations. However, as far as when we look at primordial initial conditions that didn't undergo gravitational evolution, they're also scale invariant. And so it's natural to assume that the early universe respected all of these symmetries. Can we ask for anything else? And here you can follow two different approaches, and those have been both explored in the literature in the past couple of years. Here you can assume, well, the early universe was probably close to the sitter, so I have additional symmetries. In particular, I have the sitter boost. That leads to the cosmological bootstrap, in which you harness the power of conformal field theories and of a larger degree of symmetries, and you can get very general and very powerful results. And there is a lot of beautiful work by Maldacena, Pimentel, Arcani Ahmed, Bauman, Joyce, and other people. I will not follow that route. I will follow a different approach. I will not assume anything about the sitter boost for basically two reasons. One is that they are not observed. We have no reason to believe they are symmetries of the early universe. And two is because, as I will prove in a second, if you assume those in the simplest models, you cannot, all the predictions are constrained to vanish, and the theory has to be free. So let me explain that more clearly. So I would like to state for you three theorems, and I don't have much time today to prove these three theorems, but I'm happy to give you a summary of the proof if you're interested. And these are theorems that can be proved very generally without ever writing down a Lagrangian or an action. They are valid without any further assumptions about the particle content. So any number of fields of any spin, any mass, any type of interaction, it does not matter. But as long as the theory is a single clock cosmology, then the only correlators that you can write down that are invariant under full de Sitter isometries are those of the free theory. And since the free theory is a bit boring, we will not assume that the Sitter isometries are realized. So that's our starting point. We're going to assume that the universe is invariant on translation, rotations, dilations, but we will not assume anything else. So only the observed one, which seems to be the most conservative approach if we want to make predictions for observations. It is possible that by assuming more symmetry, we will make more progress, and I would like to comment later on, since in ADS, we know that we can get a lot of mileage from assuming full ADS symmetries and having a full description of quantum gravity on the boundary as a conformal field theory, and something similar can happen for the sitter, but I'll comment on that later on. Okay, so now let's discuss what other principle I'm going to use, and then later on in the last part of the talk, I'll show you how you can use all of this principle to compute things without computing them. You just are going to write down the result, and it's going to be constrained by fundamental principles. So let's talk a little bit about locality. There are many forms of locality than what one could consider. Perhaps in quantum gravity, it's not even clear what is the correct form of locality. But in low energy effective field theories, if it is a quantum field theory, we have some notion that locality should have something to do with cluster decomposition in real space. Correlators should factorize as the product of correlators, as pointers in real space are taken apart from each other. And usually we implement this notion of locality by saying that the Lagrangian is just a function of the fields multiplied at the same point and their derivatives. I'm going to call this notion manifest locality. We proved that if a theory is manifestly local, the wave function coefficient that you compute to all orders in perturbation theory have to obey an extremely simple condition. If it is, if they are the wave function coefficient of a massless scalar field, which is what we want to predict for curvature perturbations in cosmology, their derivative at k equals 0 has to vanish. This is somehow intuitive if you think of that. If you remind this general result of Fourier transform that if you want something to decay at large distance, the Fourier transform of that has to be analytic in 0, and vice versa. So this is an analog result. So if you were to transform this to position space, it would tell you that the correlator, the connected correlator, decays as you take the points far away. But we have a precise proof of this, which is valid to all orders in perturbation theory. And it's very simple. You can write down the most generic wave function or correlator to all orders in perturbation theory has to take the form of V integrals, where V is the number of vertices, and some propagators. And then you can take the limit of one of the external energy to go to 0. You bring the limit inside these integrals. It hits the propagator. And in the propagator, indeed, there is no linear term. So the derivative with respect to any external energy, at that being 0, has to vanish. There cannot be any linear term. So the proof is very simple. There is a much fancier proof, but I think this is enough. And this is very powerful. I mean, if someone tells you, I spent the last 3 months computing this correlator, this is the result, and it doesn't satisfy this, they screwed up. I think it's very useful constraint. So as I said before, this is really the notion of manifest locality. It means that all operators that are product of fields at the same point and their derivatives are fine. However, this does not account for things that are secretly local but not manifestly local. For example, we know gravity, when you integrate out non-dynamical degrees of freedom like the lapse and the shift, has inverse Laplacians in cosmology. And so for that, we will need a more refined version of locality that I can comment on if someone wanted to know. Let me mention very quickly that this notion of locality has a very direct implications in terms of the flat space limit of correlators, which is just an amplitude. And you can understand it also in terms of the amplitude being local in a more standard quantum field theory sense. But I will not discuss this unless you guys have specific questions. Unitarity is the other big one. We think that to make mathematical sense, so to connect the mathematics of quantum field theory to a probabilistic interpretation, we need the theory to be unitary. So colloquially, probability should be between 0 and 1, shouldn't be negative or bigger than 1. And this requires all the states in the Hilbert space of our quantum field theory or our quantum gravity to have positive norms and time evolution to be unitary. So this property is respected. So colloquially, this is the conservation of probabilities. And in quantum field theories in flat space, we know its consequences. We have been knowing its consequences for more than 60 years. We know through the optical theorem in particle physics that we usually study in introductory quantum field theory courses, and the more advanced Katkowski's cutting rules, we know the consequences of unitarities for all amplitudes to all orders in perturbation theory and non-perturbatively. And this was, more than half a century ago. And yet, until last year, we had no idea what the consequences of unitarity were for something that we also measure in the sky, which are cosmological correlators. If I gave you a correlator, no one knew if that came from a unitary theory or not. And this is quite important because we think that's really a fundamental constraint on the possible result. I think that question is now has an answer, which is something we call the cosmological optical theorem, that it tells you that the correlator that comes out from unitary evolution from a Bunch-Davis vacuum they have to satisfy very specific rules. And not any function that you write of the external energies or of the external momenta that goes. That's definitely not the case. In particular, their analytic structure, when you think of them as function of their variables, where their variables are allowed to be complex, they have to satisfy very specific relations. The simplest relation that I want to show you, suppose you take a contact endpoint function. So you have n external legs, and they all come into some interaction. If you flip all the external momenta, as well as their norms, the norm would be positive definite, but if you analytically continue, it can be negative. Then the wave function has to satisfy this very simple expression. If it doesn't, the theory is not unitary. This came from a non-unitary theory. So this is rather simple, but it's beautiful how the notion of time and of unitary evolution emerges on the boundary of space-time, which does not contain time at all, right? When we measure correlation functions in the sky, we only measure spatial correlations. And yet, the analytic structure of the spatial correlation contains the notion of time. This can be extended to all orders in perturbation theory, and I just want to give you a flavor of what that result is without giving you a proof, but the proof is in the paper. So let me define this specific combination here. Let me call it a discontinuity, because it has a little bit the flavor of a discontinuity in the sense of the discontinuity of amplitude across the real axis, for example. But you can just think of this as being a definition. So that because the left-hand side is shorter to write than the right-hand side, I'm going to use this. Then the statement to all order in perturbation theory is that you take any graph to any order in perturbation theory, the discontinuity of that, defined in the previous, is equal to the sum over all possible ways to cut internal lines. There is only one internal line, so there is only one way to cut it. And a cut means that you take that line and you push it to the boundary. So this, which was a 4-point function, becomes the product of two 3-point functions. And you have to take the discontinuity of each disconnected component and put a power spectrum for every cut line. It's a relatively simple prescription. Maybe it's not so transparent, but this highly restricts the wave function that you can get. If something doesn't obey it, didn't come from unitary theory. And what we proved is that this is valid to all orders in perturbation theory, any number of loops, so it can be arbitrarily quantum. And it's valid for fields of any mass, any spin, with arbitrary interaction, and not just around the Sitter space, but any FLRW space-time, as long as it admits a Bunch-Davis initial condition. So this is remarkably general. In fact, it's just as general as we understand it in particle physics. And to me, it's crazy that such a general result had not been known for such a long time. It really means that there is still a lot of relatively simple facts about cosmological predictions that we still don't know. So 60 years later, we are starting to bridge that gap, but it's really a wide open field. And this is a very powerful result because, as you know, for amplitudes perhaps, in which you know that you can relate the decay rate of a certain process to the total cross-section through the optical theorem, something similar happens here. Loop corrections to observable, for example, the loop corrections to the power spectrum, the 2-point function, which we measure in the sky, is completely fixed by 3-level, sorry, its discontinuity is fixed by 3-level calculations. And there are many different ways to take the discontinuity, so it's actually pretty much uniquely fixed, the result that you can get. And we use this to compute the one-loop corrections to the power spectrum in single field inflation, in the effective field theory of inflation, which had not been fully computed in the literature. Only one operator had been considered, and we find agreement with that result, but we write down all possible leading cubic operators. Any questions so far?
I have a question.
Yes.
Hello. You said that when you consider the condition for unitarity, it sort of time emerges, but you said that you are considering evolution, and evolution by definition is time, especially if you consider, for instance, the concept of time by Pajer, then the time is relative. Can you explain a bit more about what really you mean by evolution and by emergence of time?
So we have two pictures here. Either you try to think of the time evolution in the bulk, and then there is time. The notion of time is manifest there in the description. That's the standard way of thinking about it.
Yes.
Or you never talk about time. You only give me the boundary correlators, and they obey this rule. This rule T doesn't appear anywhere. So I'm saying that the second way of thinking, time doesn't appear anywhere in the description, and yet it is equivalent to another description in which you do have time and the evolution is unity. So you can choose whichever description you want. They are equivalent. In the second one, time doesn't appear, but it's equivalent to the previous one. It's similar to how space appears.
Because you have considered that derivative is zero, and derivative by definition means that you are changing a bit.
There is no derivative.
Boundary, yeah.
There is no derivative here.
I just use the opportunity just to tell you that you have 5 minutes left.
Okay, sounds good. I'll move on then, and maybe you can ask me again at the end if it is still unclear.
Okay.
So using these simple rules, we can do all the calculations, some of which perhaps we teach in introductory cosmology courses, to compute correlators. But the calculations are much quicker, much simpler, and in fact do not involve any calculations. We pretty much write down the final answer because this fundamental principle constrains all the possible results of this answer so strongly. So I could be much more general and consider, for example, any number of spinning fields, gravitons, but since I have only 5 minutes, let me just talk about massless scalars, which is to some extent what we care about for the phenomenology, but this has been extended to spinning particles. And let me talk just about the 3-point function, but this can be similarly done for any other point function. So the 3-point function, because of scaling, in the sitter for massless particle, has to be a rational function. If it is scale invariant, its overall degree has to be 3. It's just fixed by scale invariant. If the vacuum is chosen Bunch-Davies, the denominator is fully fixed, can only be the sum of the norm of the external vectors to some power. Nothing else is allowed. Any other choice of the denominator violates either locality or the choice of Bunch-Davies vacuum. So this means that the only thing we have to write down is the numerator, which is just a polynomial, has to be symmetric, so can always be written in terms of the symmetric combination of the external momenta. And the only thing that there is left to compute are the numerical coefficient in this polynomial. So already the calculation of the most generic wave function, which usually requires taking the action, expanding it, computing in the informalism, some time integrals, actually has been reduced to just this numerical coefficient. And those coefficients are fully fixed by locality. If you demand this function obeys the locality, the manifestly local test that I showed you before, the derivative of this function at the origin is 0, that fixes all these coefficients. It's an extremely simple calculation, and it gives you the result for all possible bispectra to any ordering derivatives, for example, in the effective field theory of inflation, but actually it's valid for any number of fields. You can have 3 different fields, doesn't matter. And this does predict some of the most well-known observables in cosmology, like the local non-Gaussianity, which is so much sought after in large-scale structure and the CMB. That's just the solution of this equation to the lowest possible order when this exponent P is 0. And that's exactly local non-Gaussianity. To the next order, when the exponent is 2, you get something which is the non-Gaussianity in dBi inflation. And when the exponent is 3, this is the non-Gaussianity to leading order in the effective field theory of inflation corresponding to the operator phi dot cube, if you know about it. And this is sometimes called equilateral non-Gaussianity. But of course, this goes to any possible order. So you get infinitely many prediction for the bispectrum at higher and higher ordering derivatives. And they all come from this just extremely simple equation, these two. So you can see we computed them all in a page. What I think is very beautiful is that this generalizes to gravitons as well. So we now have the result that should appear soon of all possible graviton non-Gaussianities that were not known in the literature to any order in derivatives. The derivation, as you can see, is very fast, it's very quick, and there's hardly a calculation. Does not require performing any integral. Time didn't appear. I didn't have to do the time evolution to get this result. And the role of fundamental principle are very transparent. If you want to change and say, well, I don't want the bunch derivatives vacuum, then you know where to go into this derivation and change some. This derivation is actually valid for any three-level diagrams. And I don't have much time to explain it, but if you consider, for example, an exchange diagram, it has some singularities, but its singularities are known and fixed. It can only have singularities when all the sum of the norms of the vector entering each one of its vertices goes to 0. And the beauty is that all of those, or the sum of all the energies goes to 0. So there's partial energy singularities and total energy singularities. The main point, which the details don't matter, the main point is the residue of all partial energy singularities is fixed by unitarity. It just is fixed by unitarity in terms of lower order diagrams. And so if you have an analytic function and you know the residue of all of its poles, that function is fully fixed up to a boundary term. And indeed, you can write down any endpoint function in terms of lower point functions using just Cauchy's integral theorem by doing a complex shift of the partial energies, and all the residues are fixed by unitarity. And this is the result is fixed up to a boundary term, which corresponds basically to contact interactions. So this is very similar to the progress that has been observed in amplitudes, if you're familiar with it. And this predicts the trispectrum that we should measure in the CMB, just to be clear. So since I had very little time and I want to leave a couple of minutes for people to ask questions and maybe make some further comments, let me come closer to a conclusion. We want to use cosmological observations to test high energy physics and the quantum regime of gravity, at least at the perturbative. And we've made tremendous progress to really understand what the rules of the game are in general, rather than computing individual models. We finally understand unitarity, and we have some initial understanding of locality. And we understand these rules at the level of observables, right? So, which is how probably we should think about, because this is a quantum theory of gravity, the only well-defined observables live at the boundary, and so it's important that we understand the theory in terms of those boundary observables, which in principle are the only well-defined ones. We have derived a cosmological optical theorem and a test for unitarity. And all of these constraints are not only interesting at an academic point of view, but they're so strong that they fully fix the answer. So now you don't have to compute things. You just write down all possible answers compatible with that. And this predicts a large number of classical results in the literature about primordial non-Gaussianity, like bispectra or trispectra, including scalar and tensor perturbations. I wanted to mention the fact that there are much more ambitious goals of this program, and I think they tie well together with some of the topics that have been discussed in this workshop or will be discussed later. So I wanted to make that connection just because maybe it's not so transparent. So let me just discuss a couple. One is the connection to the discussion we had yesterday about the existence of the sitter, especially in a UV complete theory such as string theory. This program here gives you a completely different approach to that question that I think can nevertheless lead to a definite answer. Because if we know what are the constraints for a correlator to be unitary, all of its poles should have particles of any spin as predicted by string theory, and it should be UV complete, so that correlator should be valid at any energy. It shouldn't have, it shouldn't be a low energy approximation, so it should obey some kind of large energy limit, and it has the correct singularities. Then that's a legitimate stringy correlator in the sitter. If you can prove that that function does not exist, then you prove that string theory cannot possibly have an exact de Sitter solution. So I think that's very interesting. We're not there yet, but it is something on the horizon. Another connection is much of the discussion that we've been having about cosmic microwave background and large-scale structures, this is really a computational tool at the practical level. We can make model-independent predictions and therefore extract model-independent information from the upcoming data, either some CMB polarization, but also from galaxy correlation functions and maybe density mapping. Another discussions that we have been having was about gravitational waves, mostly perhaps late universe and of astrophysical origin, but of course there are also primordial gravitational waves, which eventually in the future perhaps our civilization will measure. And in this approach, you can really predict the most general theories of gravities, including scalar tensor theories, modified gravity, as long as they satisfy unitarity, some form of locality. So it's a strongly model-independent approach to study modifications of gravity. And finally, even most ambitiously, and that's the last thing I want to say, I really hope that this is opening the door to some understanding of quantum gravity in the Sitter space. We think we understand quantum gravity in ADS. It should be some form of a CFT. But we would like to understand it in the Sitter because that's where the universe seems to be living, and that has proven more challenging. But by reformulating all that we observed for time evolution in a way that doesn't involve time, we are actually write down the rules of this hypothetical CFT or quantum field theory that lives at the boundary. So that CFT or QFT has to obey these rules. So those rules has to come out at the boundary. And so now we have to reverse engineer what theory is compatible with things like the cosmological optical theorem that I've written down and manifest locality. And I think that's a very promising way. And a lot of people who are experts in the audience in ADS CFT, I think could really have a big impact in this field because very few people have started thinking about this from this perspective yet. So let me stop there and pause for questions. Thank you.
Okay, thank you very much, Enrico, for this very nice and clear presentation. So I guess we have a few minutes for maybe a couple of short questions. I can see people lining up for questions already. So Norma, do you want to ask a short question?
Good afternoon, good morning. Thank you very much. I have a very fast points to remarks. The first is about in your first part, the statement in one of your slides, Enrico, there is the statement, early universe is a scale invariant, or early universe is not a scale invariant, fortunately, otherwise we will not be here, is a slightly or quasi scale invariant, slightly deviated from a scale invariance, as the data have showed. And so that is in my view should be corrected, or otherwise explain it in what sense you are thinking about. The second is about loop correction and the expressions you show in the middle part. I mean the loop corrections to the power spectra from effective field theory of inflation with these said properties or answer. I should, you said it was never computed before. It was never computed before within said bootstrap approach, but it was computed before, certainly.
So Norma, I would like to hear also other questions. So if you just have comments, maybe you can postpone them to a later conversation between you and I, and maybe we can move on to questions, because I think it's more interesting to have questions that everyone get a chance. Thank you.
That's actually a good idea. Yeah, given that we have not so much time before we move on to the next talk. So Francesca, can I just ask you to step in and ask your question?
Yeah, I hope there will be a longer discussion about
there is a
time later.
Well.
So I just ask a punctual question, because I would like to understand better how this picture can be time independent from absolute time when the techniques that are used depends on the choice of a cosmology with a single clock.
Oh, no. The cosmology with a single clock was just some of the theorem that I proved early. But the results about unitarity and locality, don't rely on that. You can have as many fields as you want. The emergence of time, I don't know if you're familiar, but it's very similar to the emergence of space in holography. So in ADS CFT, you have a boundary theory that lives in one less dimension, and nevertheless knows everything about the additional dimension through some renormalization group scaling. The notion here is very similar. You expect to have some kind of boundary theory, of which I'm writing down the effective rules without specifying its fundamental definition. And that boundary theory knows about the bulk time through some properties of its correlator that only live on the boundary. So the time is emergent in a very similar way. Now, in ADS, we know the precise rules on the boundary. We know this is a CFT. It has an associative operator product expansion. It has 2-point functions that obeys with operators with conformal dimension that obeys unitary bounds, and so on and so forth. Here in the SITA, there are still some open questions, but the spirit is very similar of how we expect time to emerge. Then we can discuss on the details of what the specific rules are, but that's the direction in which this is going. And the hope is that, like in ADS, you start perturbation theory in the bulk, and that teaches about CFT with an infinite number of degrees of freedom. But then if you take n to be finite, that tells you about quantum gravity in the bulk. And if you take n to be small, that's full quantum gravity in the bulk, and for which you have no bulk description, but you do have a boundary description. The hope is the same. We guess properties in perturbation theory, and when we understand enough of the boundary theory, we're going to extrapolate it to the quantum gravity regime.
Okay, thank you. This clarifies.
Thank you very much. So I'm sorry, it's already time to move on to the next slot. So can I ask Jean-Luc to try and share his screen?
Yes, let me try.